Section 10.4 is on inscribed angles. An inscribed angle is an angle whose vertex is on the circle and whose sides contain chords. So let's take a look at a couple pictures here. So we have a circle, okay, and the inscribed angle would start here on the circle itself, go across, hit the circle on the other side, and come back this way. So notice that the vertex is actually a point that is on the circle right there. So an inscribed angle can contain the center of the circle as it does in the first example here, or the center can be in the interior of the circle as it is in the second diagram here, or the center can be in the exterior of the angle. In the exterior of the angle. So the way I like to think of an inscribed angle, first of all, you have to distinguish this from a central angle. Remember, a central angle contains the center of the circle. It's actually the vertex is the center of the circle. So it starts on the circle, goes to the center, and then comes back out. In this case, it starts on the circle, goes across the circle to the other side, and then back to this side. Here's a crazy way to think about it. You bring home a pizza from, let's say, Papa Murphy's, kind of a take and bake sort of thing, and your brother's really hungry and he wants to get the biggest slice he can out of the pizza. So instead of cutting it in the traditional way, cutting it into, the little wedges, he grabs the pizza slicer, I'll go ahead and draw it on here, and he goes over to here and over to here. And he's got his crust right here. So he has cut a really huge slice of pizza out of that Papa Murphy's pepperoni pizza just for himself. So what he's done is created an inscribed angle. And it's called an inscribed angle because it's actually written inside the angle. Okay, so make sure you know the difference between an inscribed angle and a central angle. The inscribed angle theorem says that the measure of an inscribed angle is equal to 1/2 of the measure of the arc it intercepts. The measure of the angle is 1/2 of this arc. So the measure of angle 1 is going to be 1/2 of the measure of AB. And conversely, the measure of arc AB is going to be 2 times the measure of angle 1. Now compare this to the central angle. Remember, a central angle, one that contains the center, is actually going to be exactly the same as the arc. In this case, the angle is 1/2 of the arc. And here's the way I remember it. The largest angle I can make is actually a straight angle that's 180 degrees. The largest arc that I could make is pretty much the full circle, which is 360 degrees. So the angle is always going to have to be smaller than the arc. The angle actually is going to have to be exactly 1/2 of the arc. So let's take a look at this example. Find the measure of arc XY, so that's out here, and the measure of angle ZXW. So the measure of arc XY is going to be 2 times the measure of the angle that creates it. So the measure of angle XY is going to be, the measure of arc XY is going to be 2 times the measure of angle YZ to X. There we go. Okay, and the measure of angle YZX is 52. So the measure of arc XY is 104. Now to find the measure of angle ZXW, so that's this angle over here, ZXW, the angle is actually going to be 1/2 of the arc. So the measure of that angle is going to be 1/2 of the measure of arc ZW. And we're given that the measure of arc ZW is 86 degrees. So 1/2 of 86 is 43. So it's going to take a little practice to recognize the angle and the arcs they intercept. Maybe I'll draw over those a little bit. So we have this 52-degree angle here, and the arc that it's intercepting is this right here. Remember, it might help to think of it as the pizza crust. Angle ZXW is this little angle here, and the arc that it intercepts is this 86-degree arc out here. Here's another theorem. If 2 inscribed angles intercept the same arc, then the angles are congruent. So here we have angle ABD, or angle B, if you'd like to call it that, and angle ACD, or angle C. If angle B and angle C are congruent, if they both intercept the same arc, then B and C are congruent. And I guess you could have the converse of that as well. If B and C are congruent, then they both intercept arc AD. Let me go ahead and draw that in here in color. So here we have this angle here, and this angle here, and they are intercepting arc AD. So in other words, they're sharing the same piece of pizza crust. So if two inscribed angles intercept the same arc, then the angles are congruent. Here's an example. Let's find the measure of angle R. So I'm looking for this angle right here. And I notice that both angle R, which I have this algebraic expression for, and angle S, which I have this algebraic expression for, they both intercept arc TQ. Now I don't know what the measure of arc TQ is, but I know that they both cut it off. Notice if you go T to S to Q, cuts off TQ. If I go T to R to Q, it cuts off TQ. So since they both intercept the same arc, those two angles are going to be congruent to each other. So I can say angle S is congruent to angle R, or 9x plus 2 is equal to 12x minus 13, or 3x equals 15, or x equals 5. And I had to find the measure of angle R, so plugging that back in. So 12 times 5 minus 13 is going to give me 47 degrees. So the measure of angle R is 47 degrees, as is the measure of angle S also. Here's another theorem. An inscribed angle intercepts a semicircle if and only if it is a right angle. So let's take a look at this circle here. So I have semicircle, well let's see, so angle C, which is a right angle, intercepts arc AEB. So if I go from A to C to B, and I have AB here drawn as a diameter, so it intercepts this arc, which is a semicircle, and then angle C is a right angle. Conversely, if angle C is a right angle, then it intercepts a semicircle, and that would be arc AEB. Notice that when you draw this out, the hypotenuse of the right triangle is actually a diameter, and that can be very helpful in solving some problems. Let's take a look at an example of that. So this one says find the measure of angle B, and we're given triangle ABC inscribed inside the circle, and angle A is x plus 4, angle B is 8x minus 4, and I notice that AB is a diameter because it goes through the center here. So that means that angle C has to be a right angle. So since it's a right angle, I can say that 90 plus x plus 4 plus 8x minus 4 is equal to 180. Let's see, my 4 and my minus 4 are going to cancel each other out, so then I have 9x equals, subtracting 90 from both sides, 90, or x equals 10. So the measure of angle B is going to be 8 times 10 minus 4, or 76 degrees. So again, if the triangle inside the circle has a right angle, then it's going to intercept a diameter, or the hypotenuse is going to be a diameter, and it'll intercept a semicircle, and the converse of that is also true. Okay, and I think this is our last theorem in this section. If a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. So here we have quadrilateral KLMN, and it is inscribed in the circle. All of the vertices of the quadrilateral are on the circle. This theorem says that angle L and angle N are supplementary. So remember, those two would add up to 180 degrees, and angles K and M are also supplementary. They would add up to 180 degrees. This example says find the measure of angle S and the measure of angle T. And here we have quadrilateral STVU inscribed in a circle. We know that angle V is a right angle. So because opposite angles are supplementary, well, let's see, it's given that the measure of angle V is 90. And V and S, the measure of angle V plus the measure of angle S, have to add up to 180. So 90 plus the measure of angle S equals 180. So the measure of angle S has to equal 90, because opposite angles in an inscribed quadrilateral are supplementary. I also know that angle T and angle U are going to be supplementary. So the measure of angle T plus the measure of angle U has to equal 180. Or 8x plus 4 plus 14x equals 180. 22x equals 176. So x equals 8. And then substituting that back in for the measure of angle T. T is 8 times x plus 4, or 64 plus 4, or 68. Okay. So in this section we saw a lot of theorems about inscribed angles, and actually discovered the definition of an inscribed angle. Again, lots of theorems to memorize, to learn, and to be able to put into practice in the exam.